All right, today we're going to dive into some functions that kind of live in the shadow of their super famous relatives. They're called hyperbolic functions, and you can think of them as the mysterious, kind of powerful cousins of the trig functions you already know and love. Let's get into it. I mean, we all remember sine and cosine from math class, right? They're the absolute building blocks of trigonometry. They describe everything from the waves in the ocean to the smooth rotation of a Ferris wheel. Yeah, they're old friends, familiar, comfortable, totally predictable. And their natural home, of course, is the circle. If you plot a point with the coordinates cosine t, sine t, and just let t change, boom, you trace out a perfect unit circle. And it's all thanks to that fundamental Pythagorean identity, cosine squared plus sine squared always equals 1. But then you start hearing whispers about these other guys, sinh and cosh, hyperbolic sine and cosine. They sound so similar, but trust me, they're a whole different animal. So the big question is, if the classic trig functions belong to the circle, what geometric shape do these guys call home?
Well, to find the answer, we actually have to leave the world of triangles and angles completely behind. Turns out, the secret to understanding these functions lies in one of the most important functions in all of mathematics.
That's right. Their entire identity is tied directly to the natural exponential function, e to the power of x. And this is a huge clue. You see, while sine and cosine are fundamentally about rotation and geometry, sin and cosh, they're all about growth and decay.
So let's break it down. First up is the hyperbolic sine, which by the way you pronounce as sinh. It's defined as e to the x minus e to the negative x, all divided by 2. It's called the odd component because just like the regular sine function, if you plug in a negative number, you just get the negative of the original answer.
And then you've got its partner, the hyperbolic cosine, pronounced cosh. Its formula is e to the x plus e to the negative x, all divided by 2. This one's the even component. Just like regular cosine, plugging in a negative x gives you the exact same value as plugging in a positive x. Now just look at them side by side for a second. They are almost identical. They're built from the exact same pieces. The only thing, literally the only thing that separates sinh from cosh is a single minus sign. That one tiny change makes all the difference in the world.
So, okay, we've got these weird exponential definitions. But what about our original question? Where's their geometric home? Well, let's connect these definitions back to geometry and get ready for the big reveal.
You know, as our source material puts it, the main job of sine and cosine is to parameterize the points on a circle. That's really just a fancy way of saying they give you the coordinates for any point on the circle's edge. They are, in essence, the language of circles.
And right here, this is the big aha moment. While cosine squared plus sine squared equals 1 gives us a circle, the hyperbolic identity, cosh squared minus sinh squared equals 1, gives us a hyperbola. That's it. That's their home. They aren't circular functions at all. They are hyperbolic functions, and they trace out the points on a unit hyperbola.
Okay, I know what you're thinking. That's a pretty bold claim. How in the world can those messy-looking fractions with e all over the place possibly simplify down to the number 1? It seems kind of unlikely, right? Well, let's just walk through the algebra. It is way more elegant than you might think.
So first, let's just plug in the definitions. We square the cosh term and we subtract the squared sinh term. Now, when we expand those numerators, you have to remember that e to the t times e to the negative t is just e to the 0, which equals 1. And that's exactly where those middle terms, the plus 2 and the minus 2, come from.
Now we just combine everything over that common denominator of 4. And just watch what happens. The e to the 2t term cancels with the minus e to the 2t. The e to the negative 2t cancels with the minus e to the negative 2t. All that complicated exponential stuff, it just vanishes.
And what are we left with? 2 plus 2 over 4. That's just 4 divided by 4, which equals 1. And there you have it. The identity holds. The math works perfectly. Those crazy exponential definitions really do belong to the hyperbola. Pretty cool, right?
But wait, the connection doesn't even stop with that one identity. This is where things get really fascinating. The parallel between these two families of functions. It runs deep.
This isn't just a coincidence. It's a systemic pattern woven into math. For almost any rule or identity you ever learned for sine and cosine, there's a nearly identical version for sinh and cosh.
Just look at this comparison. The derivative of sinh is cosh, just like with sine and cosine. But check out the derivative of cosh. It's positive sinh. That negative sign we're all so used to from trigonometry, it's gone. And the sum identity for sinh is a dead ringer for the one for sine. It's the same pattern over and over again with just a few strategic sign changes here and there.
So this is a beautiful mathematical pattern for sure. But you're probably wondering, so what? Are these things just a cool math oddity, or do people actually use them for anything?
And the answer is a huge yes. They are incredibly useful. They pop up in physics to describe the shape of a hanging chain or cable. You know that perfect curve? It's called a catenary, and it's described perfectly by the cosh function. They also show up in special relativity and are essential for solving certain complex equations. Even in basic calculus, they offer these elegant little shortcuts. For instance, if you had to find the derivative of the natural log of cosh of x, that looks pretty intimidating. But the answer simplifies beautifully to just the hyperbolic tangent, or tanh, of x. It's just a clean, simple solution to what looks like a really messy problem.
So I think the key takeaway here is this really deep and elegant duality. On one side, you have trigonometric functions, born from the circle, the language of rotation. And on the other, you have hyperbolic functions, born from the exponential function, the language of the hyperbola. They're two sides of the same mathematical coin, a stunning example of the hidden patterns in math.
And that really leaves us with a final thought, doesn't it? This amazing relationship was just hiding there in plain sight, connecting geometry and algebra in this totally unexpected way. It really makes you wonder, what other secret symmetries and beautiful connections are woven into the fabric of mathematics, just waiting for us to discover them? Thanks for watching.